We'll continue our discussion about statistics in design for BBE 2002. We had left off by talking about the relative frequency histogram by showing the example of the Kentucky River near Salvisa in Kentucky. Has to do with this relative frequency histogram has to do with the distribution of the occurrences of the annual maximum discharges from the period of record 1895 through 1916. This distribution helps us to understand the frequency at which certain events occurs. If we were to add up all the numbers, as I had mentioned in class, if we were to add up all the numbers, these decimal values that are shown here by these 6 bars that are illustrated here in this histogram, they would add up to 1.0. So what's indicated here is that maximum annual discharges that occur within the class interval that's associated with the midpoint 41,392 cubic feet per second. 18% of the time that flow would occur. So 18 years out of 100 basically is what we're saying the flows would be in that range. Likewise, values that would fall in the range of 94,925 cubic feet per second would occur 9 times out of 100 years, and so forth. We'll talk a bit later about the way in which we might represent these discharges such that we might be talking about exceeding a certain discharge rather than having a discharge within a given class interval. So we'll go on and talk about statistical distributions. We've talked already about a bit about probability. And here again we go back and talk about the population as well as the sample. The sample is just a portion, a representative portion of the population. It's not exactly what the population is, and that is why whatever we come up with about regarding information from the population, the sample only represents approximately what the population really is. Some common statistics that we use to measure statistics are to represent data are the mean, the variance, and the standard deviation. These are very common ones. There are other measures, but we're not going to cover them in this class. The mean is represented by x, and that it should actually be x bar with a line over the top, and mu. The x bar is the sample mean. That is, if you take a sample, you calculate the mean of that, or the average of the values, that would be the x bar, whereas the mu, that the Greek symbol, represents the mean of the population. Variances are s squared and sigma squared. S squared would be the sample standard variance, and sigma squared would be the population variance. And then standard deviation would just be the square root of those two values. From the within the ideas of basic concepts here, again we go back and talk about x as a random variable. It's a variable that is completely independent. Any number that, or any sample that you take, is independent of the next sample that you take, or any sample that you took previously to that. So the value of that variable is completely independent as a function of the order in which samples are taken. Some measures of central tendency of the values associated with that, either the sample or of the population, are the mean, the median, and the mode. The mean is usually thought of as being the average value for the sample. That would be the one measure of the central tendency of the values, essentially saying that the values of a particular variable would fall around the mean value. The median would be the value in which 50% of the values in the sample would be below the median and 50% would be above the median. And the mode would be the value from the sample that has the highest frequency of occurrence. So if you, for instance, had 50 values that were selected in a sample, you find out what value has the highest frequency of occurrence. That would be the value that would represent the mode of the data. A second measure that we might go with would be a measure of the dispersion. That is, how far apart from the that value of central tendency, whether we're talking about the mean, median, or mode, are the individual values in the sample. So one would be the range. What's the minimum and maximum value in the sample? That gives you an idea how far spread the data values are. Second one would be the variance and the standard deviation. And both the variance and the standard deviation are related to each other. Standard deviation is the square root of the variance, and that's the more common measure of dispersion, as we might call it. To quantify these measures, here we'll quantify the mean and the variance and the standard deviation. For the population itself, we call the mean, or we designate the mean to be this Greek symbol mu. It's what we call the expected value of x, where x is the random variable. So what is the expected value? Well, most likely it would be the value that is closest to the central part of the distribution. That is the value that has central tendency. And so E of x is the expected value of x. That can be calculated or represented as being the integral from the value of x equal to minus infinity to plus infinity of the integrand, which would be x, p of x dx. Here, p of x is the probability distribution function. That is this right here, is the probability distribution function for the variable x. And x is, again, as we said before, is the random variable. The variance, sigma squared, is the expected value of the difference between a value x and the mean value squared. That x minus mu quantity squared. So that's the expected value of that difference squared. And that can just be calculated as being the integral from minus infinity to plus infinity of the x minus mu squared times p of x dx. The standard deviation then is just the square root of sigma squared, which of course would be just sigma. Now, many times in statistics, or basically always, it's a good idea to normalize your random variable. So we have a random variable x, which has dimensions. For instance, if x is temperature, then it would have degrees centigrade or Kelvin, something like that. If x were a velocity, it would have units of, let's say, meters per second. If x were weight or mass, let's say if it's mass, it might be kilograms, right? Usually what we like to do is compare random variables to each other, and these random variables might have different dimensions or different units. So if we do that, we can come up with a normalized random variable if we want to make a comparison between them, and we'll call that normalized random variable z. Z is equal to the variable itself, x, minus the mean of the variable divided by the standard deviation of the variable. That gives us what's called a normalized random variable. You'll note that the value of z, because we've taken the ratio of the variable, both the x minus mu divided by sigma, it will be non-dimensional. And so then you can compare different random variables to each other if they have been normalized. Usually what we work with is the sample values of the measures, statistical measures. The mean x bar is just equal to 1 divided by n, where n is the number of values in the sample. And then you just sum up all the values of the sample. and divide that by the value of n. The variance is just s squared is equal to 1 over n minus 1 times the summation of the difference between xi and x bar squared for all the random values. And the standard deviation is the square root of s. And then the normalized random variable, as with the population values, would be just z equal to x bar, or equal to x minus x bar divided by s. That gives you a non-dimensional random variable, z. Now, the definition of probability when it comes to probability distribution functions is illustrated in this graph. Here what we've got is a p of z, where z is a random variable. In this case, maybe it's the normalized random variable. So we can imagine that we're working with x. We normalize it. We end up with a variable, normalized random variable, z. And we're plotting here p of z, the distribution of the values of z versus the value of z itself. And we get maybe a symmetric probability distribution function. So this p of z is the small p, that is this right here, is the probability distribution function. If we were to take the area of that curve, or underneath that line, up to the value z1, where z1 is just one possible value of z, this quantity here is the value, what we'll call capital P, where it's capital P of z less than or equal to z1. It's just the area underneath the curve to the left of the value of z1. That is the shaded area. This is the probability that the value of z will be less than the value z1. I want to point out here that the total area under the curve, if I were to take and add on, or look also at the part that's not shaded here, this portion right here, the total area of the curve, the shaded part and that part to the right, that area is equal to 1.0. And that's going to be the case for all probability distribution functions that we'll look at. So here I show a plot of the probability of x being less than x, capital X. We could just call this x1, which I think I haven't been completely consistent in the drawing here. But P, capital P of x less than or equal to x1. And this graph that I show here is what all integral, that is the areas underneath that small p of x curve looks like. They look like an S curve, this one right here. That's what all probability distribution functions that you might work with, they would have this kind of shape. They would start off with 0 on the left hand side, and as the value of small x increases, eventually they would reach the value capital P of x less than or x1 equal to 1.0. As I mentioned before, the area underneath the curve that was shown in the previous slide, I'll bring it back to that, the area underneath the curve is equal to 1.0. So as I allow the value of x or of z, small z, increase to the right, maybe go to infinity, the value of capital P of x goes to 1.0. So it doesn't matter what the distribution of the curve looks like, whether it's like this symmetric shaped curve that I show here, or whether it's some other type of curve, and there are a number of different ones that can be used in probability theory. And in practice, the area underneath the curve will be equal to 1.0. The shape of the curve will have this shape, this S shape, but of course the S shape can have different slopes to it, so they don't always have to look exactly the same. They'll just have a similar shape to the one that's shown here. Let's look at an example of a simple probability distribution function that's got nice mathematics, one that's easy for us to analyze, and that would be the exponential distribution function. So while before I showed small p of x to be this symmetric shaped curve, in this case the exponential distribution function is this one that I'm illustrating here. The p of x function is given here equal to b e to the minus ax, and it of course goes from a maximum value on the left hand side at x is equal to 0 to x equal to plus infinity on the right hand side here. There's a constraint on what the value of b and a, the relationship between them, has to be in order for the area underneath this curve here, this area here, in order for that area to be equal to 1, the value of b has to be equal to a. So no matter what I use for the value of b and a, or no matter what I use for the value of a, the value of b has to be equal to it. That's for the theoretical distribution function. Now we have talked about a bit about the relative frequency distribution histogram. If I had some data in which I divided the data up into class intervals and counted how many values fall within each class interval, it might look something like what's shown right here. If it looks like that, I would be pretty sure that the probability distribution function would be a exponential distribution function, because you can see that the relative frequency decreases as we go from the left hand side to the right hand side. For the exponential distribution, the sample mean, of course, is just the same expression as we have for all probability distribution functions. Regardless, you take the sample, you don't know ahead of time what distribution function is going to fit, but the mean would just be equal to 1 over n, summation of all the values of x divided over the values, over the n values, divide all those by capital N. And of course the population mean value, mu, is just the integral from minus infinity to plus infinity of x, p of x dx. And for the exponential distribution that we see above, the value of mu is equal to 1 over a, because a is equal to b, as we talked about before, or as I talked about above. And so you can go through and you can perform this integral just like you did in the second semester of calculus, derive that integration and get the result, and it will come out that u will be equal to 1 over a. For the standard deviation, we have the expression that I showed before, where s is just equal to the square root of 1 over n minus 1, summation over all n of the quantity xi minus x bar squared. And for this, the population variance sigma, or not variance, the population standard deviation is equal to the integral from minus infinity to plus infinity x minus mu squared p of x dx. And if you were to do this, where p of x was equal to this quantity here, we end up with sigma equal to 1 over a. So the mean for the exponential distribution, the mean and the standard deviation are the same value. That just happens to be that case for the exponential distribution, and will not be the case for many other distributions that we might consider. All right, so for the exponential distribution, we can calculate the cumulative probability, that is this quantity here, where p of x, that's now capital P of x less than or equal to x capital, this capital X, and we could call this just x1 because I referred to x1 before when we were doing talking about the cumulative distribution function. And so we'll call that x1, and we'll put an x1 right there. It's a fairly simple function to perform the integration on. Of course, the lower limit here is 0, not minus infinity, because the function is only applicable from x greater than 0. It's the function itself is equal to 0 for x less than 0. So it doesn't really mean anything to talk about integrating from minus infinity to 0, just because the function is 0 down in that range. If I perform this integration that I show here, the result is that the cumulative probability capital P of x less than or equal to x1 is just going to be equal to 1 minus e to the minus ax1. And so if I were to plot this function right here, I would end up with this S-curve that would go from 0 to 1.0 as x1 increases from 0 to infinity. We'll make that an x1 there. Okay, and again there's, well, this is the probability that x is less than or equal to x1. Now I will mention here that the probability then, capital P, that x will be greater than x1 is just equal to 1 minus probability that x is less than or equal to x1. Makes sense because the total area under the curve is just equal to 1.0. And so if we take the quantity to the left of x1, that is this part right here, it will just be the complement of the value of the value over here, the area on this side. The sum of those two areas, this side and this side here, should be equal to 1.0. Now, in many analyses, we want to know what the probability that x would be greater than or equal to x1 in design, let's say in a design analysis. And so we need to be able to quantify what that probability is. And so if we know what the probability distribution function is, whether it's exponential or some other distribution, we would be able to calculate what that probability of exceedance is. So this quantity that I've just encircled here is the probability that x would be equaled or exceeded, or I should say that x1 will be equaled or exceeded. We can also look at the probability that's shown here. Let's say I want to know what is the probability the value of x will fall in the range between x1 and x2. Here this is plotted as with normalized random variable z, but the z1 is equal to x1 minus mu over sigma, and z2 is equal to x2 minus mu over sigma. So here we want to know basically what is the probability that that the variable will fall between x1 and x2. We can do that, we can determine that by taking the probability that z will be less than or equal to z1, and we can determine the probability that z will be less than or equal to z2. And the area of this curve would just, or that shaded area would just be the probability of z less than or equal to z2 minus the probability that z is less than or equal to z1. So that would tell us what the probability is that the variable would fall within that range. And there may be some design analyses where you would be able to, where you'd want to know what is the probability that a particular variable would fall within that range. Now we've talked a bit about distribution, probability distribution functions. There are a lot of them. We're not going to cover but a couple of them, or we're not going to use but a couple of them in this class. One of them would be the exponential distribution I've already talked about. The second one would be the normal distribution that's shown here. It looks like a complicated formula. It's got the mean, population standard deviation in the function. What's nice here is that Excel has got a argument called norm dist that allows you to evaluate the values of the function. And we'll probably have an opportunity to show some of that in class and in lab. A second probability distribution function, p of x, that we might look at would be the normal distribution function, this one right here, where we essentially take the logarithm of the values of x, and it turns out that the logarithm of values of x has a normal distribution. So it has the same distribution as this one, but the difference is that instead of x, we're looking at the logarithm of the values of x. So that's a bit more complicated, but again, with Excel, there's this argument log norm dot dist, which can be used to evaluate the function within Excel. A couple of other distributions that we find important, and I'll speak first about the Poisson distribution, which we actually are not going to use. Maybe someday in the future we'll use it within the class, but I haven't really found a use that I want to put it to at this time. But the important one would be this one right here, which is the binomial distribution. Here we use the symbol f, small f, and this right here, the argument inside is x semicolon np. The x, it refers to the number of successes, let's say number of times a certain event occurs. N is the number of trials that were tried, and p is the probability, what we call probability of a success. And this is given by this function here, this quantity inside the parentheses, n x right here, times p raised to the x times 1 minus p raised to the n minus x. This quantity here in the parentheses is just n factorial over x factorial n minus x factorial, and all that represents is the number of ways, number of combinations of ways in which the x successes can occur within the n trials. A very simple example application of the binomial distribution, and here I talk again about what this function means. An example would be the probability of having exactly 3 heads come up in 10 tossings of a coin. So you take a penny and you toss it 10 times. What's the probability that you get 3 heads in the 10 tossings of the coin? Now there are a number of ways in which those 3 heads can come up if you did get the 3. One could occur on the first toss, one could occur on the 5th toss, and one could occur on the 10th toss. Or one could occur on the first toss, one could occur on the 3rd toss, one could occur on the 8th toss, and so forth. That's what this function right here, this quantity here, accounts for, is the number of ways in which the 3 heads could occur within the 10 tosses. Putting in the value of x equal to 3, the number of times, let's say you have a success, that you have 3 heads, and n is the number of, or 10 is the number of trials, and then 0.5 now is the probability that in any given toss there's a 50% probability that it will be a head. So if we were to substitute those into the formula, I get a probability of occurrence of 0.117. There's a probability that you'll get exactly 3 heads in 10 tosses. A probability of 0.117. Now if I were to do the calculation for variable number of x's, of course if there's only 10, if there's 10 tosses, then you can only get a maximum of 10 heads. What's shown here is the binomial distribution, considering possibility of 0 heads in 10 tosses, 1 head in 10 tosses, so this would be 0 heads in 10 tosses, 1 head in 10 tosses, 2 heads in 10 tosses. There's the one we just calculated. 3 heads in 10 tosses was a probability of 0.117. And so you can see that there's a probability of about 0.24 for 5 heads in 10 tosses, and so forth. So that's the binomial distribution function for having X tosses in 10 trials, given that the probability of a head in any given toss is 0.5. The probability of getting 10 heads in 10 trials or 10 tosses is just given by the same formula. So we put X is equal to 10, and you'll see you get a 10 minus 10 in the denominator. 10 minus 10 factorial is just 1.0. If we were to calculate that out, the probability is 0.00097. A fairly small probability, though, you'll get 10 heads in 10 tosses, and that's what this number is right here. So we can use this binomial distribution in many ways within both industrial design, let's say the BPE type design kind of things, but also in EEE if we're looking at hydrology type of questions, water quality types of questions. We might be interested to know, for instance, how many times a 100-year flood is likely to occur within a 50-year period. Each year is one, in that case, each year is one trial. What's the probability that you'll get, let's say, 300-year floods within a 50-year period? That's an important question when it comes to designing infrastructure. Same kind of question could also be asked for industrial applications. Another important aspect in design is uncertainty analysis. We'd like to know how much error there is in a particular quantity. So I'll give you an example of this here in a moment, but first we need to define the mathematics of this. So given that G, let's say, is a function of a number of variables or parameters. So G is just some function, and it's a function of the variables or parameters x1, x2, x3 up through xn. The error in that function, that is the error in the value of G, based on expected errors in the values of the parameters and variables, xi's, that error can be calculated with the formula that's shown here. So delta G, which is the error in the value of G, is just going to be equal to the summation of the relative change, or let's say the dependence of G on each of the variables xi, times the error that you might have in the measure, or the uncertainty in the value of the individual values of the xi. So this quantity here illustrates or quantifies the sensitivity of the variable G with respect to a particular variable or parameter xi, and this quantity here represents the uncertainty that you have in that particular input variable or parameter. So we can sum these up and take each of those quantities here, you take the square of it, then you sum all those up and take the square root, and that gives us the error or the uncertainty in the output of the variable that we're interested in, or the function that we're interested in. So now what we'll do is we'll look at this at a application. It's going to be a EEE application in this case. So let's look at we're interested maybe in evaluating or estimating the discharge in an open channel. Let's say that we have a rectangular, or let's say not a square channel, but a rectangular channel. It's got vertical sides, a flat bottom to it. It's got a certain width and a certain depth to it. And we have measures of variables and parameters for that channel at a number of different locations in the channel. And what we want to do is we want to be able to estimate what the discharge is in the channel from those measurements. So let's go through formally to try to quantify the function that we're interested in, the parameters and variables. So the discharge in an open channel can be represented by the empirical formula, Manning's equation. That is, Q is the discharge is equal to 1 over n times A times R to the 2/3 times S0 to the 1/2. Here n is Manning's roughness coefficient. S0 is the longitudinal slope of the channel. It's just a dimensionless quantity, so many meters per meter of channel length. A is the cross-sectional area of flow. That's got square meter units, and then R is the hydraulic radius, which is just the area divided by the wetted perimeter of the channel, which again would have, or now would have, units of meters. For a rectangular channel as shown here, the depth is equal to y and the width is equal to w. And of course the depth and the w would vary depending on where you're making the measurement. The W is the bottom width, or the width of the channel, has units of meters, and Y is the depth of flow, has units of meters. So the area, according to those definitions, would be equal to W times Y, and the hydraulic radius would be equal to area divided by the wetted perimeter. The wetted perimeter is just the wetted surface of the channel, which would be equal to W plus 2 times Y, the two sides of the channel. So our discharge, according to Manning's equation, given here, if we substitute in the area, the hydraulic radius, into the formula, it's just going to be 1 over n, W times Y, and then Wy over W plus 2Y raised to the 2/3, S0 to 1/2. And that can be simplified down to be this formula right here by combining terms. Alright, so our first order error analysis in the estimate of the discharge Q is just going to be equal to Q equal to dq dn delta n plus dq dy delta y plus dq dw d delta w plus dq s0 delta s0. And this is somewhat of a mistake, because this should be squared. This should be squared. This quantity here should be squared, and this quantity here should be squared, and we're taking the 1/2 power of that sum. So in order to start this analysis, we need to determine these derivatives. Okay, everybody knows how to take derivatives because they've had calculus, but here recognize that this is a partial derivative, which basically says that we're taking the derivative of the function q, which was defined on the previous slide, with respect to n, and all that varies in that derivative is the value of n. Everything else in the formula, the w, the s0, the y, all remain constant. So when we do that, we end up with that quantity there. If we were to take the derivative of q with respect to y, the n remains constant, the s0 remains constant, the w remains constant. The only thing you're taking derivative with respect to is the variable y. And that gives us this result here, which is not simplified yet. It's just written out in longhand. We can do that for dq dw and dq ds0. Each time, the partial derivative just means that the function is varying with respect to the particular variable that the derivative is being taken with respect to. All other variables in the formula remain constant. Okay, so just to go back, we would take each of these derivatives once they've been quantified. We'd substitute into here the values of, let's say if we take this first one, the QDN, we'd substitute in the a mean value of n the mean value of W, the mean value of Y, the mean value of S0, quantify that to give us the partial derivative. And then we'd multiply that by that quantity by the quantity that's here, so the delta n, which would be the uncertainty or the error in the measurement of the value of n. So somebody goes out and measures the value of n, they get some error, they get some mean value of n, and they get some range of the value of n. You might take the upper and lower limits, you might use the standard deviation of the values, and you'd use that for the value of delta n. You take the product of the dqdn with the delta n, square that, and you're going to do that same thing for the other variables, dqdy, dqdw, dqdz, s0, and you're going to be multiplying them by the errors in those individual parameters, squaring all those, summing them, and then taking the square root, and that'll give you the, in the end, what it'll do is give us the uncertainty, the error in the value of q. So the value of q that we would come up with would be some mean value of q. It'll be greater than or equal to q plus, or sorry, minus delta q less than or equal to q plus delta q. So the range that you see there for the value of q would be the range over which we would expect to find the correct value of q, but we're not certain which one it's going to be. We'll do a class example showing the exact application of the formulas that I've just shown you for the open channel. The same kind of analysis could be applied to many other EEE type problems, but also to BPE type of analyses as well. The last topic I want to just briefly touch upon this idea of Six Sigma, which is an industrial standard that's used in the BPE arena. This will be covered in much more detail in a lecture later on by a guest lecturer by Dr. Omar Espinoza. But the Six Sigma is the idea that was put forth in industry. It's a quality control concept. Here TQC representing total quality control or total quality management. It's a concept that is set up for defect reduction. And the aim with this is to, and again this is mainly for industrial applications, the aim is to reduce the number of defects that you would have in an industrial application or manufacturing to 3.4 defects per million options or opportunities. So if you were to produce 1 million widgets, whatever they might be, you're saying that you don't want to have more than 3.4 defects. That's a fairly strict requirement. The method that's used here is called DMAIC, or in longhand would be define, measure, analyze, improve, and control. And within the idea of Six Sigma, this is a probability distribution function. We can call it F, or we can call it P. What we're saying is that it's going to be a very tight distribution such that the most of the values of your product will have a value here within this range that would be within the desirable range, and that very few of them would fall out here. So let's say that right here, this is the mean of the desired characteristics of a product. Let's say the size of the product, or maybe the weight of the product, the functioning of the product. And what we want to do is we want to minimize the range over which the values of that characteristic occurs. And the Six Sigma essentially means that we want to be able to maintain essentially almost zero probability for values to occur on the tails of this distribution. So that provides for a high quality condition. And with the Six Sigma condition, Six Sigma requirement, it is set such that very few values will fall outside of the desirable range, and the very few we're saying is 3.4 values per million opportunities, or three out of each 1 million entities or products that are produced. And with that, we'll end this video. There will be an example application in class of the that open channel error analysis for open channel analysis.